And then we'll go ahead and get started here. Okay, keep in mind that we have the recording going on, so if there's anything private that you want to discuss, if I can get you guys to wait until after we end the recording, we can talk about that. All right, I'm gonna go ahead and try my best to finish some of the background information in chapter 3. The way it looks like it's going, I'm gonna have to come back again on Friday to kind of finish up chapter 3, and then we'll try to move into the some of the key points in chapter 5. So we're okay. This is the fact that this is kind of how things will go this time around. So last class, if you guys remember, we are talking about conformations, and conformations are just preferred orientations. And that's very important because when we start to think about organic molecules in a realistic sense of how they look in nature, how they look in solution, right? How they look in if they're gases, we need to think about how atoms are arranged. So we talked about two main different classes of organic molecules, acyclic versus cyclic. You guys told me that acyclic molecules are those that are not in rings, and cyclic molecules are those that are rings, all right? So when I'm not in a ring, how are my atoms arranged? We talked about the main feature are just being these rotations. Molecules are not this, I guess, frozen in space. Instead, they have enough energy at room temperature to wiggle, spin, rotate, etc., right? And we've learned that the way that atoms like to arrange themselves in bonds is where the atoms attached to two neighboring carbons are staggered, right? That's the preferred conformation. And we realize that there are other conformations that are present, and we need to study those, but the preferred conformation is the staggered one. However, we can rotate where atoms are eclipsed, and those are unpreferred or not preferred conformation or higher energy conformers, right? And we talked about something being a anti-staggered, which is the lowest possible, where my two largest atoms on the two attaching or the two bonded carbons are farthest away from each other, right? 180 degrees. We talked about something being total eclipse, where my two largest atoms on my two bonded carbons are directly in front and behind of each other. Then we talked about also in staggered conformation, there could be ghost interactions that raises the energy. And we talked about there being other eclipsing interactions that are not the total eclipse, and there'd be a little bit lower energy than that total eclipse, all right? So we want to have a firm understanding of the differences of those conformations for acyclic compounds. When it's something that's staggered, eclipse, total eclipse, or anti-staggered. You want to be comfortable with that and the relative energies of those conformations. Then we talked about the other class of organic molecules, those are those in rings, all right? We mentioned that there's a phenomenon called the ring strain, right? You guys want to be comfortable with that. What is ring strain? Anyone in class can chime in. What is ring strain?
Combination of angle and the torsional strain.
Okay. Say that one more time. Okay. Okay, I can give me 1 sec. Somebody in class can't get in, so let me call Ms. Johnson here.
I don't know if you're sharing your screen, but I can't see it if you are.
Yep, I should be sharing my screen. Okay. I'll stop and reshare. Oh boy.
These people saying they can't get in.
All right, they're gonna have to tell me names. I can only call them, but you got to tell me right now the names.
Yeah, they typed in the chat, but Jada and something.
What's the last name on Jada?
Curry.
All right, I'm calling Jada Curry. Who else?
Jatavian Smith.
Smith. All right, I'm calling Smith. Sorry, with my current setup, I'm not able to read read messages without breaking the presentation that I'm trying to present. All right, I'm just sharing my screen, so I already had that first initial call. I'll say it again. If you can hear and see my screen, would you mind raising your hand? And if you can't, this would be the best time to tell me. All right. Okay, I got one hand, so I'm assuming that everyone can see and hear. All right. If not, please speak now. I got the recording going, so just in case something happens, please just feel free to go back and look at the recording. All right, so moving forward one more time, acyclic versus cyclic. All right, you guys should be comfortable with all the possible acyclic conformations. And I want to say this for this class. I know it's difficult with the virtual teaching. Trust me, I know. But there has to be a responsibility on you guys' side to use Pearson. There's post and pre-questions, right? Personally, on my side, if I had to assess this class, I don't think you guys are doing a lot of independent study, right? I don't think you guys are using those tools to the best of your ability, right? So if I'm mentioning learning acyclic conformations, and I haven't released any of the problem sets or quizzes yet because I got a lot of issues with Canvas. Canvas is just getting revamped on my side. All right. So until I can get that together, I'm ask you guys to hold off. But you can use Pearson, the post questions. I don't even grade them. They're there for practice. You can just screen for any Newman projection question, confirmation questions, shared questions that we're going to cover to make sure you guys have this stuff down, right? So please feel free to use that. You guys have an e-text as well. You're more than welcome to use those type of materials to assess and to make sure you guys are growing, right? Everybody knows this, right? There's no way you get good at something without practice, all right? That's just how the world works. You want to be good, you practice, right? But if you don't want to be good, I understand too. If you just want to get by, then, you know, you can get by just doing the bare minimum. But if you want to excel, definitely take advantage of those tools, all right? So I'm hoping everybody is growing comfortable with those confirmations. On the second side, if I'm not acyclic, I am cyclic. All right, and somebody so adequately, or so appropriately just told me about ring strain. They told me that ring strain is a combination of two things. You confusing in the class, sorry. Those two things are gonna be angle strain and torsional strain. Angle strain comes from the fact that when I have to make certain rings, my bond angles are deviating. All right, so we said that the deviation is the greatest in the 3-member ring, the 4-member ring is deviated, and the 5 is pretty much the closest it can be. But the 6-member ring is okay. There's no significant angle strain there. All right. Also, we talked about torsional strain, right? Torsional strain comes from bonds that cannot rotate out of eclipsing directions, right? So that bond is becoming very, very strained. We call that torsional strain.
Dr. Cooper,
And the
I have
3-member.
a question.
Go ahead. Yes, ma'am.
Is the acyclic, cyclic, the
Cyclic.
one that's in the ring, that's where the boats and stuff come in?
Those confirmations, yes, but that only the boat is only for the 6-member ring.
Oh, okay.
Okay. Good question. All right. So for the 3, there's no known conformer. It's just a 3-member ring. That's it. For the 4-member ring, it could pucker, right? So that's its preferred conformation. It's to pucker out to alleviate some of the eclipsing. For the 5-member ring, there's an envelope. That's the preferred conformation at 5. And what is the preferred conformation for 6-member rings?
You said a boat?
It's right here on the slide. It's the chair, right? The chair conformation is the preferred. All right, so keep in mind, these are all the possible conformations, right? So we talked about like acyclic, having that eclipse. That's a possible conformation, but it's not preferred, right? We said that eclipsing is bad. So chair has 3 other, or 6-member rings, has three other conformations: a half chair, a boat, or a twist, right? Those are other potential conformations. But the preferred conformation is the what? The chair, all right? So keep that in mind. Out of all possible conformation, the highest in energy is what?
A half chair.
The half chair. That's right. The half chair is the highest energy conformer. Just like if we looked at the acyclic eclipse or the total eclipse, that's the highest there. For the six-member ring, the highest is the half chair. Okay? Next in energy will be the boat, and the last in energy will be that twist. All right? And something that we didn't mention is that there are two chairs, and we're going to move into that today, right? So that means out of two potential chairs, sometimes there's one chair conformation that's preferred over the other. All right, so that's our last discussion in this chapter. If I had to investigate my two chairs, which one would be preferred? Okay, so we're going to move into that today. We're probably. Okay, can I say that one more time? Say what point?
Share your screen.
Can I explain?
Can you reshare your screen?
Okay, can I reshare my screen? Oh boy. Okay, I'll try to do that again. All right, I just reshared my screen. Can you guys see my screen now?
Yes.
Okay, great. So half chair highest, next in energy, boat, next twist, last chair. We mentioned that there's two potential chairs. You guys want to start to look at these. This chair on my left-hand side is leaning towards the left. The chair on my right-hand side is leaning towards the right. That's how we know that these two chairs are different, right? There's a ring flip or a chair flip that's occurring here. What you guys want to look here is that in this structure, carbon 1 is on the bottom, but in the ring flip, carbon 1 went up to the top, right? So it's almost like this carbon has been pulled up and this carbon 4 has been pulled down, right? So that is a conformation that happens among two possible chairs. We'll come back to that closely. Let's go back and talk about the chair conformation. This is the most stable. Why? There's no eclipsing and the bond angles are preferred. They're ideal at 109.5. All right. So this is the only conformer for six-member rings where I don't have eclipsing interactions and I don't have deviated bond angles. So the chair is preferred because of that. Let's look at the other conformations really quickly. The boat. All right. The boat has some bad interactions going for it, right? If I look here, and if you want to look at these two hydrogens right here, I don't know if you guys can really see them, all right? They're going to be eclipsing each other, all right? So there's these eclipsing carbons and atoms present, right? These two H's, this is even better to see, I'm sorry. This H and that H there, they're eclipsing directly in front and behind each other, right? So there already are some bad sterics, all right? Also, these flagpole hydrogens, right? Right up top. They are closer to each other than ideal. They don't even want to be that close. But because of the way that the boat is bending or the conformation that it takes, this is a bad interaction, all right? So this is not preferred, and this is why the boat becomes the second highest in energy. If I look at the twist, however, the twist isn't too bad, right? However, there are some bad interactions. If I look closely again, these H's here are kind of overlapping, so they're not bad, but it's trying to pucker itself to alleviate a lot of potential staggering interactions, right? So it's okay, but not as good as a boat conformer, right? So we know that these eclipsing bonds results in torsional strain. Again, because those atoms cannot rotate out, they build up torsion, all right? The twist has fewer eclipsing bonds, all right? And it doesn't have that flagpole. That's why it's lower in energy than the boat, all right? And this is the energetics that we covered last class and we also talked about today, okay? So very important today. We need to start to discuss these positions on the ring. All right, there's two position terms that we use. Axial, which is along the axis that's always vertical to the ring, and equatorial, that's also horizontal to the ring. Right, so we want to make sure we're comfortable with that. Axial position versus the equatorial. And this is the first time I taught this without drawing these on the board. So we're gonna see how this goes. But I have some slides that I'm building now that I think will help on Friday's class. So we'll wait until that. But today, I'm gonna go ahead and use this to at least introduce those topics. All right, so if I look at this molecule here in red, all right, these are all the axial positions, all right, and they're vertical. I'm thinking that everyone's comfortable with that. And everything in green here is the equatorial, all right? So the first point that I want to make is that the axial and the equatorial are not equivalent positions, all right? So sometimes placing things axial is preferred, and then sometimes placing things equatorial is preferred, all right? So we want to make sure we are comfortable with knowing which way is best for the ring that we're looking at. So why is all that important, all right? This is important because you're going to have to start to investigate ring flips, all right? So that means that this 6-member ring chair can flip to this 6-member ring chair, all right? And I want to make sure I go back and talk about how this happens, all right? So typically a 6-member ring here, the chair will move into a half chair, to a twist, a boat, a twist, another half chair, and finally a chair to move between these two conformations, all right? All that detail isn't really important right now, and I'm not gonna ask you anything relating it to that sequence. I'm not gonna ask for you to know chair, half chair, twist, boat, twist, half chair, and then the chair. But I want you guys to know that all these conformations have to, you kind of move through all those potential conformations to get between these two chairs, all right? So if I look at my first chair conformation and look at this methyl group, all right, this methyl group is going to be in this axial position. Always, this happens in every ring flip. When I flip from this chair to the next chair, now the methyl group substituent is going to be in an equatorial position, right? So that's the first thing that you guys want to start to put together when you do ring flips, is that if a substituent is axial in one ring, when I flip it, it's going to be in the opposite position. It's going to be equatorial now. Okay. Any questions there, Ms. Johnson and Claire? You got any questions? All right, no questions. I'm looking at faces. I can kind of tell if there's questions that come up. All right. So in this chair here, I got axial, and in the other chair, I got equatorial. All right. So I'm going to give you guys now your first clues in determining what's going on between these two chairs. Large substituents prefer to be equatorial. If you haven't, please make a note of that. Large substituents prefer to be equatorial. I'll say it one more time. Large substituents prefer to be equatorial. All right? So if large substituents prefer to be equatorial, which chair is the preferred chair, right? So we said that the chairs are already the best conformation, but chairs comes in sets of two. There's going to be two potential chairs for every 6-member ring. Which chair is preferred? Is it the one on the right or the chair on the left? Anyone that's brave enough to speak, please do.
Dr. Cooper, you are losing me.
Okay, I'm losing you. What am I saying that's losing you?
You saying axial and equatorial, and I'm lost.
Okay, you lost on axial and equatorial, right? Can you see that this bond on this carbon is vertical? Can you see this bond on this carbon is equatorial? All right, so before.
It's just going too fast.
Okay, I'm going too fast. All right. I'll try to slow down. Okay. I'm trying to slow down. All right, can anyone tell me which chair is preferred? Is it the one on the right or the chair on the left?
The right.
Okay, Somebody said the right. Show of hands. Who believes that the chair on the right-hand side is the preferred chair? Yeah, good. I got about 5 hands up. That's good, right? So just off the knowledge that I gave you, if I had to put a constituent, this methyl group equatorial, or if I had to put the methyl group axial, you would choose the one that's where? Equatorial. So that's correct. This chair is the preferred chair. And and I'll ask you why. Why would that be the case? You'll tell me what?
The largest on the
Yeah, the largest constituent is on the equatorial position, right? That's the reason why that chair is preferred. We got the space model here. Let's figure out why. If I look at this methyl group right here, right? And I had to investigate any interactions, maybe it's seen some of these axial green hydrogens, and maybe it's pretty close to these equatorial red, but I need to look at the other conformation to confirm. If I look at where the methyl group is axial, I'm starting to see something, right? These methyl groups are really hitting these red axial ones, right? So this becomes a bad interaction right up in here, right? Right where my mouse is located, all right? So placing this thing axial puts it in a position where it's going to be closer in contact with other axial constituents, all right? However, if I place this thing equatorial, it's kind of out there by itself, right? It's not really seeing these green or these red hydrogens as much as they are in this position here, all right? So the equatorial position will be preferred for larger constituents, all right? I'm going to move forward here. This is telling you what's going on here. And this could be tough to explain. They're trying to switch back to Newman projections, and I'm not going to ask you guys to move from a chair into a Newman projection, so you're okay. But it's just trying to tell you that when it's axial things, there's some ghost interactions that can arise between this methyl group and carbon 3, but it also should be between carbon 5 as well, right? However, if I go equatorial, right, I'm now anti to 3, right? If you look here, these are anti, and we know that the anti-staggered conformation is preferred, right? So this is why placing things in this equatorial position will be preferred in these type of conformations, all right? Let's talk about a very bad thing that happens, all right? There's something called a 1,3 diaxial interaction, all right? So if I label this carbon 1 right here, this will be 1, 2, and then 3, all right? If you have an atom axial here and an atom also axial on carbon 3, I get something called the 1,3 diaxial interaction. This is the one that I was trying to describe in the space filling model, right? That methyl hitting that red methyl. Let's go back to that. All right, right here is my 1,3 diaxial interaction, right here, right? This is a bad interaction, right? Typically people write sterics like this, all right? This causes this conformer to be less preferred. Instead, it's gonna ring flip, right? It's gonna go through the half chair, then the twist, then the bolt, then the twist, the half chair, and another chair to get this conformer. And this conformation is gonna persist. Now I have my large constituent equatorial, okay? So if we look at the energetics here, this is more stable by 7 kcals per mole, right? Or you want to use kilocalories, you can as well. All right, so this means that placing this large group equatorial is preferred. All right, any questions there so far? I just want you guys to take home that point, that placing larger constituents equatorial is going to be the preferred conformation that these rings or these chairs like to have. Okay, no questions.
Wait, okay, so you said we will or won't have to do those?
You will and won't have to do, you need to know that larger constituents equatorial will be preferred.
Well, yeah, I'm talking about the whole 1,3 diaxial.
Yes, you should know, you should be able to identify a 1,3 diaxial interaction.
If that's the case, can you
go over it like really quickly, like one more time?
Okay, sure. All I did here is look for atoms 1 and 3. Let me get a marker, let me get a pen if I can. This is atom 1, 2, and 3. Right? Atom 1 has an H axial here. Again, axial is everything that's vertical. And it has this methyl group that's also axial, right? These two groups are going to interact with one another in a bad conformation that's just labeled as the 1,3 diaxial interaction. All right, so the take-home point is this. 1,3 diaxial interactions, if you have them, are bad. And typically the only atoms that can have them or be just between two H's. All right, so typically, if you looked at, if I had to count 1, 2, 3 again, right? This H and this H is also axial, right? So that's also a 1,3 diaxial interaction. This is the smallest possible one you can get. So this one just, you can survive having this type. But to put the methyl group axial here is not a good thing. It's going to be interacting severely with that hydrogen. All right, so this is why I get this 1,3 diaxial interaction. So placing things actually in the axial position typically rise or gives those 1,3 diaxial interactions, right? There's actually 2 of them here. I can go this way. I can also say 1, 2, 3 here, right? And this H is also interacting with this, right? So I got 2 1,3 diaxial interactions that are causing this chair conformation to be higher in energy than when I can alleviate that by moving this into the equatorial position. Does that help answer the question? That's a tough question. It's just something that I just feel like you just have to be able to recognize. I just see that this is axial and that is axial, and I know that's going to lead to a 1,3 diaxial interaction. That's just what we call it. That's the name of it. It's just an axial atom at carbon 1 and an axial atom at carbon 3, they're going to interact. All right, and that's going to be not preferred, sterically bad. Any questions there?
Dr. Cooper, Kayla just texted me and said she was having trouble getting in, and then I went to the lobby and she texted like 15 minutes ago and said she was having trouble getting in.
What's her last name?
Kayla Jones.
All right, I'm calling her right now.
All right.
Okay, good. Let's keep moving over with this. So this slide is trying to show when I place a certain atom axial, and again, if I put it axial, it's going to have that 1,3 diaxial interaction, right? It shows you the influence of the size in the interconversion between putting this thing axial and it flipping to get it out of axial to be equatorial, right? So if I look at the fluorine, the energy between the two chairs are kind of close. But if I come down to like a tert-butyl group, right, the energy difference is huge here, right? So placing a very big tert-butyl group here is going to cause this molecule to be extremely destabilized to favor the ring flip to where the axial position is converted to equatorial, right? So just really trying to get you guys to think about those type of things. All right, any questions so far? Again, what we're trying to build a understanding of right now, just at the fundamental level, is that there's 2 potential chairs that I always have to investigate. So when I ask for the lowest possible conformation, you want to make sure that you're choosing the correct chair because there's 2 of them, right? And the best chair out of the 2 will have the substituents, the largest substituents in equatorial positions, all right, if possible. That's not always the case, but if possible, you want to place those substituents in equatorial positions, okay? The reason why is because I can alleviate very bad 1,3 diaxial interactions, right? So having my group axial and having it axial to another hydrogen or another atom is going to be very bad, and that could be a big issue. Okay, good. So let's take a look at this molecule called cis 1,3-dimethyl cyclohexane. All right, we're gonna try to break these down a little bit further next class. I do need to talk about how we can draw these, and I got to do this from PowerPoint from some stuff I'm gonna work on. Okay, so if I look at the two chair conformations here, right? I have the first molecule here on my left-hand side that I got a methyl group axial and another methyl group axial, right? And from the slide, it's very easy to see that that leads to a very bad wet 1,3-diaxial interaction, all right? Instead, I ring flip and both of my axial positions become what now? Equatorial, right? And now this ring is highly preferred. So 1,3-diaxial interactions don't have to always be interactions between a sustituant and a hydrogen. In this case here, for this molecule, it needs to be coming from two methyl groups that are interacting unfavorably with each other, right? And we see that this prefers to be in this conformer, right? So what becomes very important when we start to discuss these is that we need to know how to draw a cis 1,3 dimethyl cyclohexane, right? And what does cis mean again? Did we talked about this? Yeah. What does cis mean?
The same.
Same side, right? So if I had to draw this 6-member ring, I had to put, if I drew one methyl group on the top face, the other methyl group had to be drawn where? Also on the top, right? So this is why these two methyl groups are here, right? When I ring flip, they're still on the top position. I'm going to teach that next class, what it means to be top and what it means to be bottom. But in this case here, these are both also on the top face, but now they are equatorial top, and this is preferred. So if I go to trans 1,3-dimethyl, what does trans mean now?
The opposite side.
Yep, opposite, right? So if I look at position 1, and this is 3 right here, right? If one position has a sustituant top, or in this case it would be methyl, the other position has to have that sustituant where? Bottom, right? So I got one axial and one equatorial. And if I do the ring flip here, this axial becomes equatorial, but the original equatorial now becomes what? Axial. And if I had to ask you to tell me which chair is more preferred, this chair or the ring flip chair, what will you tell me? You would tell me that they're both the same energy, right? All right, and why was that? In the first chair, I have one axial and one equatorial. And in the other chair, I also have the same thing, one equatorial, one axial, right? So they both have the same exact energy. Sure, there's a 1,3 diaxial interaction here, right? And it's the same thing down here, right? A 1,3 diaxial interaction here. They both have them. There's no way we can alleviate it because we started off with a trans molecule, right? So in this case here, the two chairs are equivalent. So you want to get used to that fact. Are the two chairs equivalent, or is there one preferred chair over the other? All right, let's take a look at cis 1,4-dibutyl cyclohexane. All right, so what's going on here with cis? They have to be on the same side. So here they got one carbon or one tert-butyl group on the bottom. They got another one on the bottom, right? But this is equatorial here, and this one is axial, right? And if I want to ring flip this, right? How can I do that? How can I ring flip this? What would happen? Say that one more time.
I was just saying this boat.
Yeah, that's right. Yeah. This is a twist bolt here, but to be able to move this into the next confirmation, I got to go through all my other confirmation. Half chair, twist, bolt, twist, and then back to a chair, right? In this case here, we mentioned that having any one of these positions or torpedo groups axial is not preferred, right? This is the worst 1-3 diaxial interaction you can generate. So this one is cool, it's equatorial, but this one's axial, right? So what ends up happening for cis 1,4 diturbutyl cyclohexane, instead of having a chair conformation, it actually adopts this thing here, which is a twist bolt. And why do you think it prefers to be in a twist bolt conformation?
The energy.
Well, the fact that it alleviates any one of these groups being axial, right? So this thing is kind of leaning to the side, which is equatorial. Again, equatorial is along the plane, right? All right, and this torpedo group is also equatorial. So this is the only conformation that allows both of these torpedo sustentrians to be equatorial. If I ring flipped it into the other chair, this will move axial and this one will move equatorial. So I still would have one torpedo group axial. So to alleviate any of these being axial, I had to ring flip to this, or I had to, yeah, ring flip to the twist bolt. All right, so this gives you the one exception of a molecule to where the chair is not the preferred conformation. All right, any questions there? Okay. Let's try to do this problem and then we'll look at the key. Can we draw both chair conformations of cis 1,2 dimethyl cyclohexane and determine which conformer is more stable? And then we also will do this for the trans version, all right? And then we're going to predict which isomer, the cis or the trans, is more stable. All right, so let's draw this molecule out first as a 2D line angle structure. I would draw 6 members in the ring, right? Oh boy, this looks weird. I'm sorry. Okay, you know what? Let's work on the computer. 1 sec, I'm gonna switch over to drawing program.
That's how I'll be trying to draw it.
Sorry. That's funny. That's how it looks. I know it's tough to draw on the computer. It really is. Okay, I should have Kim draw open. All right, let's draw both chair conformations for cis 1,2 dimethyl cyclohexane. So I want to first start off with a 2D representation of that. So I know that cyclohexane is a what? 6-member ring, right? And on positions 1 and 2, I should have a what there?
Dimethyl.
Yeah, I should have methyls there. Okay. So my 2 methyl groups have to have a relationship to each other. I'm going to go ahead and draw my methyl groups in first. Is everybody okay with me saying ME, right? To make this cis, they need to have what orientation on the ring? They need to be on the same side or on the opposite side?
The same.
The same side, right? So we talked about that a wedge can mean the front or the top, right? So I can either write 2 wedges or I can do 2 what?
What was the other one?
2 dashes, right?
Yes, it's
That's right, 2 dashes. In this case, it doesn't matter, all right? And for me to tell you that I wanted the 2 dashes or the 2 wedges, you have to wait to chapter 5 to get that type of information. I would have to tell you something about the stereo centers to be able to determine that information. But just the word cis is just relative information. Just in comparison to each other, they need to be on the same side, all right? So there's no way we can differentiate between these two for this. And for the chair discussion, it's fine to use either case, all right? So I'm hoping everybody's comfortable with this right now, that we could draw this molecule out. Yes, ma'am.
Kayla said she was kicked out again.
She was kicked out. Okay, I could try to call her back.
All right.
Give me 1 sec. Okay, I just called her. All right, so now I'm just gonna focus on this chair. I'm gonna put a box around it because it does matter initially when you guys are learning these that you would want to focus on one of the two. They don't look equivalent from the start. So this is focus on this chair now to draw. All right, so we said there's 2 potential chair conformations, right? Updating mode. Okay. I can't see the full screen. Give me 1 sec. All right, I got it. Sorry. All right, we said there's 2 potential chairs, right? There's one leaning towards the right and the other is leaning towards the left, right? So these are my 2 potential conformations I can have. All right, I'm gonna borrow my numbers here. All right, I'm gonna call, I like to start with my upper right-hand carbon and I like to go clockwise. All right, so that's gonna be carbon 1 and that's gonna be carbon 2. All right, I'm gonna talk more about this next class, but any carbon that's pointing up, and I know it's hard to see pointing up because typically I can show my hands and I can't do that right now, but this is pointing up, I guess. Let me see if I can try to draw that on the screen here. I can't see any of my arrows. All right, give me 1 sec. I gotta take it out of this screen here. Oh, come on. Okay, so if we look at this carbon right here, if you look at how the 2 lines, I put this little gray circle here to indicate the carbon, that carbon is pointing up. Right, so because it's pointing up, the axial position at a carbon that's pointing up is also the up or top position, right? So that means wedge, right? And the equatorial position is going to be down or bottom. That also means dash, right? So maybe I should write that in here. This is dash. Wedge, right? So this is what you guys want to get kind of comfortable with when I look at these chair conformations. If the carbon is pointing up, then the straight line up will be for the top. And equatorial will just mean the bottom. If my carbon is pointing down, like this one right here, right? Okay. Can everybody see that pointing up and pointing down? If I look at carbon 1, what will you tell me? Is carbon 1 pointing up or pointing down?
Pointed up,
That's right. Carbon 2. Is carbon 2 pointing up or down?
down.
Good. This carbon right here. Up or down?
Which one?
The carbon that I'm pointing to right here.
That down?
No, that carbon is pointing up, right? The two lines are raising up.
Oh,
All right. This carbon right here, is that pointing up or down?
I can't see your cursor.
Down.
That one's pointing down. This one should be pointing up. This is down, and this is up. All right, I'm gonna try to do this again on Friday. We'll try to break down what is pointing up and what pointing down. However, if I'm pointing down, all right, that means that axial is down now, right? So it flips. So axial means down or the bottom. That's the same thing as saying dash in my 2D structure. And my equatorial is now all right, I said some weird words here. This should be front or top. This should be back or bottom. Back or the bottom. This should be the front or the top. Okay. So if I look at carbon 1, I think everybody saw that one because it looks just like this one. It's pointing up. And up top, we said that we're going to put this on a wedge. So I have to put my methyl group on in what line? An axial line or equatorial line? An axial line, right? That's going to look just like that, right? And if I had to look at carbon 2 here, right? It's also on a wedge, right? Which indicates the front or the top. And carbon 2 is pointing down, however. So if I want to put front on a carbon that's down, I have to go where? Axial, equatorial. I have to go equatorial, right? So I go there. So to draw cis 1,2 dimethyl cyclohexane, this is the way I draw it, where there's a axial position on carbon 1 and an equatorial position on carbon 2, right? And I have to do my ring flip now, right? So in my ring flip, my 1 moves down here. My 2 now becomes over here, right? I still have to have the same relationship. They still have to be wedge and wedge. If I don't do that, I'm drawing a new molecule. So what is the top for carbon 1 now? Equatorial, right? And what is the top for carbon 2? Carbon 2 is a carbon that's pointing up. So the top here has to be axial, right? So if I had to ask you, which chair is more preferred, what will you tell me?
They're both the same energy.
Yep, they're both the same energy. Very, very good. All right, I'm just trying to put an A for axial here. This is probably, I don't got time to do it like I want. And again, I know that could be tough. You guys are saying this is a lot to get. Friday, we're gonna try to break this down one more time, all right? It's just easy to do this drawing than it is virtual, right? This is something that I typically would draw out and I can talk in class. There's no way I can safely teach all of you guys this semester like that. So, build some slides. All right, good. So these two things are the same energy. And that's really good that you guys can see that, right? One of these is axial and the other one is equatorial. Same energy. All right. If I had to do this for the trans version, I know my time is almost up. I'm going to do this quickly. I'm just going to focus on one of the trans. I'm going to make the first one wedge and the second one dash. All right, so now this is trans 1,2 dimethyl cyclohexane. And if I had to investigate my two chairs, in one of my chairs, again, I'm going to start carbon 1 here. I'm going to put that on an axial because it's wedged up. But carbon 2 right here is on the bottom, and the bottom from that carbon is right here, right? So that's a carbon that's pointing down already. That's the bottom, right? And if I did my ring flip, my carbon 1 would be equatorial. My carbon 2, which is the bottom, is going to have to be also equatorial. So I got 2 equatorial bonds in one molecule. And 2 what bonds in the other molecule? Axial bonds, right? So which conformer is preferred?
The right.
Yeah, bingo. Ah, I didn't keep it right
Okay,
here.
so this is about the same energy, but when they're trans, the one that has the large substituents that are on the equatorial that has the most energy.
Yes. Yes, you're saying the right thing. Give me 1 sec. I'm trying to get my arrow to work here. But that's right. When I have substituents that are axial, right, that's going to cause the energy to rise. So the other one has both an axial. I can't get my circle, but I'll just write up over the top. This is the lowest energy conformation. This is most preferred. There's not 2 R's in there. I don't know. Okay, is everyone kind of comfortable with that? I'll go back to the PowerPoint slides and then we'll end. That's like the last point. Let's just go look at the publisher slides from when I was making. If I can, this computer's acting up already. I'm sorry, just hang in there a little bit longer. I know I'm over. I'm sorry. It's my computer just. Oh boy. Just play this for me, please. Sorry, that's a different class. All right, if this works, we'll try to get it to work. Okay, good. Hopefully you guys can see my screen. All right. If I can move forward. All right, so we said that this is the cis version, gave us 1 methyl group axial, the other one equatorial. This is equatorial, right? So they have the same energy. However, if I do the trans version of this, right, I get 2 axial and 2 equatorial, and we realize that having our things equatorial is preferred. So that makes this, or the right side of this equilibrium, the preferred molecule. Okay, is there any questions with that so far? The last part of this question is describing which of the 2 would be more stable. All right, we realize that the trans would be the most stable, right? Because it allows the opportunity to put 2 substituents equatorial, whereas the cis would have at least 1 equatorial and the other one axial. Any questions with that so far? This last statement is very important though, when I try to ask you to compare. Cis and trans are distinct isomers. They cannot interconvert, right? So I can't go from cis to trans. If I started off with cis, 1,2-dimethyl, I have to make sure that all my atoms remain cis. And if I start with the trans version of that, all my atoms have to be trans, all right? So we're not saying that the cis interconverts into the trans. We separate those two things from each other. But if we had to say if the cis or the trans isomer is stable, we will say that the trans isomer is more stable because it will afford the 2-methyl groups to be equatorial in one of the chairs versus the cis. Okay, very good. All right, next class, we're gonna do a mini review. That's what I had planned in my notes. We're gonna review a little bit of naming, a little bit of acyclic conformations, and then we're gonna touch up our chair conformations. And then we're gonna move into chapter 5 and really talk about stereochemistry. All right, we need to start getting into that before the weekend. There's probably gonna be a study module this weekend on stereochemistry that you guys would cover. All right, I'll talk more about exam 1 on Friday as well. I'll be able to release the key then. I got 2 students that are working in the background to try to make sure they can finish taking the exam. And we apologize, it's taken a long time just because of all the issues and things that are coming up with Canvas and all that. But I should have that worked out by Friday. All right? If anybody, give me 1 sec and I'll take your question. Anybody else that needs to talk to me before then, if you can just schedule some time on Thursday, that would be great. Okay? At that point, I guess after this line, this is it. That's the last thing I needed to say. So class is over for today. I'm going to go ahead and stop the recording and also take the attendance. And then I can take your question. I'm so sorry. But thank you guys for joining in today. All right, any questions? Go ahead. Give me 1 sec. Can I stop the recording and then I'll take your question?
Okay.
I'm sorry. I just wanted to end the class so everyone could move on. All right, stop the recording. Yes.